and down. Amplitude, there is no amplitude because there is no maximum or minimum point. So very different from our, cosine sine functions. All right. Let's see, what's this next part here? Here we have graphing reciprocal trig functions. So graphing our reciprocal trig functions. So that's like cosecant, secant, and cotangent. So reciprocal mean 1 over. Reciprocal has a vertical asymptote at each 0 of its primary trig function. So anytime sine is 0, cosecant has an asymptote. Anytime cos is 0, secant will have an asymptote. Anytime tan is 0, cotangent will have an asymptote. The reciprocal has a 0 at each vertical asymptote of its primary trig function. So if there is a vertical asymptote, basically only for tan, then the reciprocal will have a value of 0 at that point. Has the same positive / negative intervals, but intervals of increasing and decreasing are reversed. Important to note. Y values of 1 and -1 do not change, and therefore this is where the reciprocal and primary intersect. Local min points of the primary become local max of the reciprocal, and vice versa. Okay. So let us graph a little bit of this, shall we? Okay, so here we have, complete the following table for cosecant x. And cosecant x, remember, has to do with sine, right? So this is our sine curve right here in the dotted line. This is sine x. So sine of 0 is 0, sine of 90 is 1, sine of 180 is 0, sine of 270 is -1, sine of 360 is 0. Pretty straightforward, and then obviously you just follow the main points going backwards. Main points. The first thing that you're going to do is anytime that your primary function has a 0 point, that is an asymptote. So always draw your asymptotes first. So here we go. Asymptotes, asymptotes, asymptotes. Oh, and there's one in the middle. There you go. All right. So we got 5 asymptotes right now. 1, 2, 3, 4, 5. What else do we know? Well, I guess we should plug in these values here, right? And if you're not sure, the way to do that is to make your sine x function. Which, you know what? I'll grab right now since we have it here. So here we have sine x, and we're just gonna do the flip. The reciprocal. So 0 over 1, this is going to be 1 over 0, so it's undefined, of cosecant. So cosecant of 0 is undefined because sine 0 is 0. So then the opposite, or the reciprocal, is undefined. Now, when it comes to sine x of pi over 6, that's 1 over 2. So cosecant is going to be 2 over 1. Pretty straightforward, right? 2 over 1. Next, we have pi over 3, which is 0.87. So what's 1 divided by 0.87? Because remember, this is over 1. Just flip it. And if you flip it correctly, you should get around 1.15. 1 over 1 is just obviously 1. This is going to be 0.87. It's the same value as the one above, so it doesn't change. 5 pi over 6, well, that's 1 over 2, so that's obviously the flip of that is 2. 0, anytime there's a 0, it's undefined. We know that because 1 over 0, you can't divide by 0. Negative 1 over 2, so the flip of that is -2 because it's just -2 over 1. And then here we have negative 0.87, which is the same thing as negative 1.15. And then we have -1 because it's just 1 over 1. Then we have negative 1.15. Then we have -2, and we have undefined. Okay. So time to get rid of this. Let's graph this. And we'll use purple. So we have our vertical asymptotes. Pi over 6, which is here, which is equal to 2. So 2 is here. Pi over 3 is 1.15. So that's 1.15 right there. And pi over 2 is 1. And that's where they intersect. at a local max or min point there. And we have 1.15, and then we should probably have this too. And we know it's going to go like this. Okay. What about the second half part? Same thing, kind of, sort of. Let's see, we're at 7 pi over 6. So 7 pi over 6 is negative 2. Negative 2 is here. I'm pretty sure it's going to be there. Pretty sure it's going to be there. Pretty sure it's going to be here. It's going to be here. Negative 2 for 11 pi over 6. Yes. It's going to look like this. Okay, and that's what it looks like. And I can fairly confidently say that the other points here are going to look like this because, you know, it kind of follows a pattern here. Okay, this is very poorly done, but you get the idea. And there you go. That's cosecant x. Pretty straightforward, hopefully. And let's see. Let's go over the properties of cosecant x. Domain is XCR because, once again, it goes all the way to the left, all the way to the right. But remember, it can't equal certain points. And those points are x cannot equal k times pi, where k is any integer value. So any value or factor or multiple of pi, so 0 pi, 1 pi, 2 pi, 3 pi, negative 2 pi, it doesn't exist. So x cannot equal those values. Range, same thing. Except one thing you've realized is that if you look at the purple graph, the reciprocal function doesn't go between these values. It doesn't exist. It does at the same point, except for, you know, the ones. So except for that one point, it doesn't really exist in the middle here. So our range is going to be from y has to be less than or equal to -1, or y has to be greater than and equal to +1. Period is 2 pi because it repeats every 360 degrees or 2 pi radians. And there's an amplitude because there's no maximum or minimum. Okay, pretty straightforward stuff. Let's move on. We're going to do the exact same thing except now with secant. I'm not going to go into too much detail with this since it is very similar, just like cosecant was. So I will show you the graph. I'll show you that same values, 1.15, 1, 2, undefined, -2, and so on. And if you look at it, the asymptotes are there whenever cos would be 0. The red function is your cosine function. So cosine function starts at a maximum, goes down to 0, then -1, then 0, then 1 again. And obviously, if you're going in the reverse direction, you can do that as well. And your reciprocal function will always look like this. And always intersect at that one local maximum or local minimum point. And there you go. So that's the graph. We're gonna move on. And here's the properties. Very similar properties to the cosecant function, except when it comes to our undefined values, it's pi plus 2k pi over 2, because it's the multiple of pi over 2, essentially. Pi over 2, then we have 3 pi over 2. So pi over 2 plus 2k pi, where k is, you know, integer values. Range, the exact same thing as cosecant, which is y is less than or equal to -1, or y is greater than or equal to 1. Period is exactly the same, and there's an amplitude. Similar stuff. Now, cotangent is where it gets a little bit different. So cotangent, let me just grab that for you. So this is where it gets a little bit trickier. All right, so here we have our tan function. How do I know it's our tan function? Easy. Because, well, it has vertical asymptotes, which aren't really drawn here, but I will fix that. Oh, I know why. Because we're going to graph the other one here. Okay, yeah, so I should not put these in right now. But for now, these are the tan function, and it has asymptotes at 90 and 270 whenever cos would be value of 0. All right, so tan function, this is what it looks like. What would the reciprocal of a function that looks like this look like for us? Well, let's just get the values from tan. Because we did a graph for tan x, right? And we'll just take the reciprocal. And remember, inverse and reciprocal are two separate things, so don't confuse the two, please. So tan is 0. So anytime your primary function is 0, the reciprocal would be undefined because you're just doing 1 over 0 then. You're dividing by 0. Here, this is 0.58. So what do we do? Well, what is 1 divided by 0.58? Now, it says 1 over root 3 because you can do exact values, right, for these values. So if you want to do that, you can just write root 3. But we're more interested in the actual point, so I'm going to write 1.73, which is root 3 approximated. Pi over 3 is root 3, so that's just going to be 1 over root 3, or 0.58. Now we have undefined. So wherever the primary is undefined, then the reciprocal is going to be a 0 value. Kind of have that, you know, I guess yin and yang thing going on where whenever one's undefined, the other's 0. And then where's 1's 0, the other's undefined. So here we have negative 1.73. So, you know, 1 over that, which is going to be negative 0.58. And then see 1 over negative 0.58. It's going to be negative 1.73. 0, 1 over 0 is undefined, so this is going to be undefined. Then we have 1.73, 0.58, 0, because tan is undefined, so yeah, 0. Negative 0.58, negative 1.73, and undefined for the last one. So these are our cotangent. So I'm going to erase these, and I'm going to make new asymptotes at these values. So at 0, there's going to be an asymptote whenever tan is 0. So it helps that they already graphed our tangent function, because whenever tan is 0, you will have an asymptote for cotangent. Okay, this is cotangent. And now, what does the graph look like? Well, pi over 6 is 1.73, so 1.73 is going to be here. Pi over 3 is 0.58, so that's going to be like halfway. Then we have a 0 value. Right, pi over 2 is 0. And then we have 2 pi over 3, which is negative 0.6 essentially. And we have negative 1.73, so that's like there. If you haven't figured it out, looks like that. Kind of going in the opposite direction, if you can imagine that. So let's see, 7 pi over 6 is 1.73. That's here. This is probably going to be 0.58, most likely. This is going to be 0, 0.58, negative 1%. Yeah, it's kind of just dancing. I don't know if you guys can see it. It's kind of going like in this direction. Yeah, so that's cotangent. So tangent and cotangent, you can see that they look very similar, except they're kind of, I guess, facing the different direction, you could say. All right, and the last thing is properties of the cotangent function. Same thing as tangent, where the period is pi radians. X cannot equal, or x is all the real numbers except it cannot equal k pi. Y is all the range, and there's an amplitude. And that's it.